So here we go, and today I'm here to give you an introduction about what an attribute encryption is and how we can use it to make the searchable encryption schemes. But basically, first of all, we should know what searchable encryption is. So I'll answer that question also, and this will be our agenda for discussion today. I'll be introducing first what searchable encryption is, why we need actually the searchable encryption, how we can construct these schemes. Then we go to the formal definition. We'll see its general framework and the security definitions associated with it, and what things we need to take care while designing such scheme. And then we'll finally come to the attribute-based searchable encryption schemes, in which I'll take two schemes. And these two are my paper only. And here we'll discuss how we actually the research issues that we have in attribute-based encryption. So how we resolve those. Okay. So this will be our agenda. So first of all, what searchable encryption is basically a technique through which one can perform a search over the encrypted data. And you don't have to disclose any information about the underlying plain text. And it enables a third-party cloud server, like we have stored our data to third-party cloud server. So it enables them to perform the keyword-based search on our behalf, on the behalf of the data user, without even asking for the secret key. Means everything that we do is in the encrypted domain or in the ciphertext domain we are doing. And in addition to its direct application in searching the encrypted data, searchable encryption has also basically changed the way any encryption technique can work. Generally, if you know that when you might have worked with lots of encryption techniques, so they either completely decrypts the data or it do none of it. This makes them quite unsuitable for the situation where we need only a part of the data that needs to be decrypted. So to design such a flexible system, the searchable encryption techniques can be used, and through which we can search that particular part of the encrypted data, and thereby we can achieve partial decryption also. Now, this is what searchable encryption is. Now, what is the motivation behind this? As you are aware that cloud computing nowadays is one of the most promising technologies, because it has fundamentally changed the way we store and access our data. In cloud, the storage and management of the data are delegated to some third-party remote cloud server. So that's fine. It unburdens us from the overhead of local storage and management, and moreover, it adds flexibility, affordability, availability. It provides so many things to us, and more organizations are shifting towards the cloud paradigm. However, apart from these benefits, there are some security concerns associated with the data stored over the cloud, because the data is held onto a remote server and we cannot fully trust that server. So one obvious and very straightforward solution that comes to our mind is we should encrypt our data first and then we have to store it. So that's fine. It definitely solves the issue of data privacy. But it will beget another problem. Now, as we know, searching is one of the most basic operation. So there arises a need of a technique that should be conducive for the search operation, and at the same time, it should ensure privacy of the data. And the secure searchable encryption schemes are answer for this need. Now, building the searchable encryption scheme, we can use either the symmetric key encryption or the public key encryption techniques. So if we use symmetric key setting, then the corresponding searchable encryption scheme is called symmetric searchable encryption. So with this, this type of searchable encryptions are very fast and quite easy to implement, because it involves very less computation. But on the downside, the symmetric searchable encryption schemes, they involve a very complicated process of key sharing. When we consider the multi-user shared storage environment, like in the cloud, basically we have multiple users. So in that case, it suffers from a very complicated process So to make this process simple, the idea of using the public key setting was introduced, and this was first done by Dan Bonnet in 2004. And he gave the first public key encryption with keyword search. He named that scheme like this. So here, anyone who can see the public key of the intended recipient, he can send that message, or we can encrypt using the public key, and later on that intended recipient will can decrypt using its decryption key. So we have a pair of key here. So whenever we talk of the multi-user shared storage environments, so there the public key setting is a preferable choice. So from now onwards, we'll discuss only the public key based schemes. Now, if we discuss the formal definition here, so as we know, searchable encryption the encrypted data without disclosing any information about what is being searched. Now, to enable the search over encrypted data, so what data owner needs to do, a data owner needs to create a searchable ciphertext. Okay, so we have a set of data files with us, which are represented here by the capital letter D symbol, and each of the file has a metadata associated with it. We call them as a set of keywords, and it's not like we can randomly assign any keywords, or we can randomly choose any keywords. They are chosen from a well-defined a universal set we define for them. So all the searchable encryption, because of this we cannot like choose any random keyword here. Because of this, all the publicly searchable encryption schemes, they suffer from that offline keyword guessing attacks, because we have this finite set, and adversary can perform this guessing attack on us. But that's a separate issue. But here, to create the searchable ciphertext, we encrypt these keywords using some public parameters, and then that index that we got is uploaded onto the cloud server along with the reference to each of the data file. And then the data user will search those keywords. So everything is done based upon the keywords. So it's not like directly we are, each of the data file is associated with the set of keywords. And whenever we want to search something, then you have to generate something. Later on we'll understand that it is we call that as search trapdoor or search token. So using that, the cloud server will perform search on our behalf and give us the corresponding file. Now, this searchable ciphertext, which we call that as index also. So usually two kinds of approaches are followed to generate the index. First one is the straightforward approach. We call that as forward index, in which the index is built over the data files. So for each data file, we have set of keywords associated. So everything is encrypted, data file as well as the keywords. And to encrypt the data file, usually we use symmetry key encryption because they are fast. But to encrypt keywords generally, because we want to make them searchable in a multi-user scenario. So generally we use public key encryption scheme here to encrypt the keywords. And in the inverted index approach, we build the index over the keywords. So for each of the keyword, we'll store where that keyword is, whether that is contained in data file 1, and means corresponding data files are stored with the keywords. So that is the two approaches we have. So these are there, these are like inherent in the scheme. We don't explicitly mention that how we have built the index and how these things work. There is a mapping. This mapping exists. The key focus of searchable encryption schemes is on how to encrypt these keywords so that we can later on search them without decrypting them. And we don't have to do that task on our own. It has to be done by the cloud server, some third-party server, and give us the corresponding data file to us. Okay. So is there any doubt or I should go? In general, in any searchable encryption scheme, there are four party involved. One is called the trusted authority, which generate the all the credentials, which issue all the credential to the all the data users, to all the parties, the data owner and the data user. Data owner is the one who wants to share his or her data to other users, and he encrypts the data and the keyword and upload that to the cloud server. Now, whenever some data user wants to access some data, wants to search some data, then he or she will issue a search token query or a trapdoor, we say, because that is means it is without this trapdoor, the cloud server cannot perform search over the encrypted data. So it's like a backdoor that we give to the cloud server, some access capability we give to the cloud server. But with that, it can only perform the search, but it can tell you that whether that file exists or not, or give the relevant reference for that. But it cannot get any information about what we are searching for. And finally, after performing the search operation, the cloud server will return the search result to the data user. So this is the general system model we have. And the general flow of the scheme is like the trusted authority who issue the all the credentials to the all the users. So to do that, it usually run two algorithms. One is called the setup algorithm, which will take in the security parameter that will decide the security of the scheme, the length of the keys that we are going to use in the scheme. So using that, it will generate the public parameter, which is available for all, and the master secret key, which will be kept by the trusted authority only. So that master key will be used later on to assign the credentials to the all the cloud users. So to assign the credentials, this trusted authority will use one algorithm called key generation. So it takes into the input this master secret key and it will output the secret key to the data users. It could be data owner as well as the data user. And whenever the data owner wants to share its data to the cloud server, then to do that, we use one algorithm called it will basically encrypt the keywords that I was mentioning earlier. So we call that algorithm as generate index algorithm. So it will take this public parameters that are available to all, and using the public parameters, it's not like a public key that is specific to some user and for that user this data is intended to. No, this is a shared cloud storage environment. So with the general public global parameters, the data owner encrypts the keyword and upload that to the cloud server. Now, we call that as the encrypted index. And this is encrypted index is nothing but the ciphertext corresponding to that keyword. So that's why CI for WI. And at some point, some data user wants to access the data. So to do that, he will generate a search trapdoor or a search token we sometimes call, using his secret credentials, and he will generate the trapdoor for some particular keyword. And that search token is then given to the cloud server, and using the ciphertext that is stored over the cloud server and the search token that the cloud server just got from the data user, if the keyword is same in both of these two, the ciphertext and the trapdoor, then the cloud server will return one, that the keyword that we have searched for is found, and otherwise it will return 0 if it won't exist in any of the corresponding data files. So this is the general flow. Now, in we have to ensure the security of these schemes. So the general security definition that we take into this is adaptive chosen keyword attacks, CKAs, I forgot to mention the full form here. It's chosen keyword attack. So here basically the adversary, it actually choose two keywords of its choice, and we call them as challenge keywords. And it will give those two keywords to the challenger that will encrypt those two keywords using whatever scheme you have defined. And then the ciphertext, by looking at the ciphertext of the two keywords, the adversary should not be able to determine that out of those two keywords which is this keyword, means which one is the corresponding plain text keyword for that. So this is what we have to ensure. And there is another popular measure of security. We call that as selective CKA. So before this we have a security game here. So before that start here, adversary have to commit to the these two challenge keywords. Means at the beginning of the game, not at the challenge phase, but at the beginning of the game, the adversary have to commit that I'm going to later on ask for these keywords. So okay, I'm sorry. So this is the basic model, the flow of the scheme, and the security definition that we follow in the public key based searchable encryption schemes. We haven't yet come to the attribute based searchable encryption schemes. We are just discussing the general public key based schemes. Now, while developing the searchable encryption schemes, there are three main research challenges. The first one is efficiency, security, and query expressiveness. So efficiency of the searchable encryption scheme, it is measured in terms of the computational, this and the communication cost, we can say. And this computational cost, it is estimated in terms of how many operations are required to perform a particular task, the type of operations required to generate, let's say, the ciphertext, the search trapdoor, and finally to perform the search. And similarly, the storage cost is the cost that is measured in terms of, that is measured in terms of memory space needed to store the ciphertext or the search trapdoor, the public parameter, the secret key of the user. So whatever storage cost is their size basically determines the storage cost we need for that. And the communication cost is calculated in terms of amount of time required to send the secret key, because it is generated by some trusted authority. We need to send it to the all the cloud users. So how much time it is taken to send the secret key, to send search trapdoor from user to the cloud server, and then the result from cloud server to the user. So that is the communication cost we measure. And searchable encryption scheme, we say that it will be efficient when if all these associated costs are reduced to a minimum. So we aim to develop an efficient searchable encryption scheme where we try to reduce the computational overheads. So the two schemes that I'm going to discuss today, so they are based upon efficiency. They are actually dealing with the efficiency aspect. Next research challenge is the security. And security of a searchable encryption scheme is measured in terms of how well the scheme hides both the data file and the associated keywords. Now, it is assumed that a scheme is more secure if the adversary is more powerful. And how we measure the power of an adversary? That is measured in terms of what facility we provide to her, like access to several Oracle, what type of query she can ask. And moreover, if we use a weaker security assumptions in our security proofs for the searchable encryption, then we say the resulting scheme is more secure. Because the time cost of breaking the weak assumption is much greater than the strong assumption. So the strong assumptions are relatively riskier, we can say. And these weak assumptions are the well-known standard assumption that we incorporate while generating the ciphertext to ensure the security. And finally, the query expressiveness. So the query expressiveness of a searchable encryption scheme is measured in terms of the variety of search queries supported by the scheme. And the expressiveness may vary in terms of it could be simply an equality query, or it is a multi-dimensional range query. So depending upon that, the efficiency of the scheme also varies. So basically, there exists a trade-off between these three parameters. A more secure scheme may be less efficient and vice versa. And similarly, a scheme that is that's more expressive search query that would be less secure, or that would be less efficient. So we have to actually balance these things off. So we have to decide what our priority is, and accordingly we aim to develop the searchable encryption. So now let's come to the key part here. As I said in the beginning, we are going to discuss attribute-based search encryption scheme. Now here, like I said, to generate the intents, we have just used public parameters and encrypted the keyword using that. Now here, if I want to provide the differential searching capabilities, or if I want to say it like I want to provide the fine-grained searching capabilities, is depending upon some credentials, I want to vary that this person should be able to decrypt this much, and if he or she is able to satisfy these many conditions, then means I want to put that now to the fine grain level. So for that, in a differential manner, if I want to share my data onto the cloud server, then for that the answer is attribute-based encryption. So here, basically, we have two variations. We have a ciphertext policy attribute-based encryption and key policy attribute-based encryption. Now, in ciphertext policy attribute-based encryption, the policy is associated with the uh, uh, ciphertext. Okay, we might have seen this step here. If I use the along with the public parameter the access policy along with it to encrypt the keyword, then the resulting encryption is called as ciphertext policy based ABE. So we have used policy with the ciphertext. So that's why ciphertext policy. And if we use the policy for generating the secret key of the user, then in that case we call that as the key policy attribute based encryption. So the example that I have drawn here is the ciphertext policy ABE. So we'll take a we are going to take two schemes. So one will be key policy attribute based encryption is based upon the key policy ABE, and other is based upon the ciphertext policy ABE scheme. So when the policy is associated with the ciphertext, we call that as ciphertext policy. So for example, here, the user has certain credentials. We call that as it possesses some attributes. For example, you see here that civil engineer and PhD. There is some student who is in the whose branch is civil engineering and doing PhD. So these are the credentials or the attributes of that user. And similarly, we do have some other users with the credentials. So you need to send the credential to the trusted party or key generating authority. So that will take public parameter and master secret key and this credential of yours, and correspond to that, it will generate the secret credentials for that user. And what the encryptor or the data owner will do, so you now add this fine grainness to the access capabilities. So for that, it's like the result of civil engineering branch is out, and we want only those students to decrypt the data. So what we can do is we can encrypt that marks file with the given policy that if it is a civil engineering student and he could be from he could be doing MTech or PhD. So only those candidates will be able to decrypt the ciphertext because for in we have used this information. So here only and the two users U1 and U3 will satisfy this access policy. So only they will be able to decrypt and get the corresponding score file. So that is the general idea of attribute-based encryption. Now, in attribute-based encryption schemes, we have an inherent computational and storage cost associated with these because we are now adding the attributes or the policy into the ciphertext. So the ciphertext size and even the computations involved in that will vary according to the number of attributes in the policy. That will no longer be constant thing. That will become a variable, and that variable is they vary in terms of the number of attributes contained in the access policy or the number of attributes possessed by the user. So the aim is to resolve this. We want to use fine grainness, but we don't want to increase the associated cost, the storage and computational cost of the ciphertext for generating the what we say a search wrapped or for searching the keywords. We want that to be constant. It should not vary as per the number of attributes. So this is the key agenda that we are going to take right now. So this is the first scheme that we'll discuss, in which we'll be using attributes, but the size of the secret key and the search trapdoor will be constant. It will not vary with respect to the number of attributes. So let's discuss the key highlights of this scheme. So this is a searchable encryption scheme, or we can say fine-grained searchable encryption scheme. So basically, it's the combination of attribute-based encryption and searchable encryption scheme. Now, it of course inherent all the benefits, that is the fine-grained access control capabilities and expressive searching capabilities are provided in a multi-user environment, in the multi-user cloud storage environment. And here, basically, we have used the key policy design framework. So the policy, the access policy, which we'll discuss by taking one example, that is associated with the secret key of the user. And here we have one more benefit that if we want to add any attribute or delete any attribute, so that could be done effortlessly. Means it support frequent changes with minimum number of computations. And this is the main highlight, that it has constant size secret key and search trapdoor. It will not vary with respect to the number of attributes. And further, it has constant number of pairing operations in the search algorithm. So in the test phase, we have constant number of pairing operation. It is also invariable of the number of attributes. And since pairing is a very costly operation, by linear pairing, so hence we can say that our scheme support fast search. And to construct the scheme, we have used, I have mentioned, we have to use some security assumption, and weaker or standard assumption are generally better. So we have used here for the construction, this is a linear assumption. Now, first of all, let's see the access policy here. So the access policy that we have used is a tree data structure. We have used basically the tree data structure to represent the access policy, where if you see all the leaf nodes, they represent the attributes possessed by the user, and each non-leaf node is a threshold gate. Okay, and this is the access policy, and this is the T gamma we call as a access tree associated with the given policy. And here, the type of the threshold gate, it is determined by the number of children of that node. A threshold gate for, if I say ki, a threshold value is 1 for any internal node, then that will represent an OR gate, because we want just one attribute to and that will return true. If it is equal to the number of children of that node, then it represents the AND gate. Okay, so because for that, if it is 2 here, so that will be AND gate. We want to be true, then only it will be true. Okay, so depending upon that, we have certain threshold values, and this is the access policy represented by this tree diagram here. And to get the secret, we have used the bottom-up approach, and normally the approach is top-down. We assign one secret to root and all the attributes. So that will actually be the reason of having the variable cost that is proportional to the number of attributes. But we started in the reverse manner. We assign the secret credentials, a secret value to all the attributes here, and we go in the bottom of fashion, and here we have constructed that is used as an as a basic value for constructing the scheme. Now here in the construction part, we have basically these many algorithms. A little detail of these algorithms is also shown in the coming slide. So first of all, we have again the same kind of setup algorithm we have. So this algorithm will take again the security parameter, the attribute universe. So in addition, and using these, it will generate the public parameters. And the public parameter will be used later. Basically, it is used everywhere. Here also in the search phase. And master secret key will be used by the authority to generate the credentials for the users. And we have one build tree algorithm, which will build the tree that I have shown. It will take the access policy in, and it will output the that access tree that I have just shown you earlier. And here we have this key generation algorithm. So it again takes the public parameter, master secret key, and the access policy. And as you see here, the access policy is associated with the secret key of the user. So that's why it is called key policy based searchable encryption scheme. So the underlying AB scheme we have used is KPAB. And here we have another
But how the threshold value will be distributed?
So it basically generates the index for the keyword, and that keyword is encrypted under the set of attributes. So this is the set of attributes. So if the reverse thing happens, so here to generate the secret key, we use a set of attributes of that user. And here, if we have used the access policy, then that will become, so the underlying framework that we have used is ciphertext policy attribute based encryption. So this is basically the change that will happen in both the schemes. So here we have used key policy attribute.
Hello.
Finally, to first token, we have this trapdoor algorithm. So a public parameter and transport the keyword W, and then the search will again be ciphertext encode the corresponding search. And this is the basic, what we can say, the detailed construction of our scheme. So here we have used the bilinear NAM, and basically, so we have here the two groups, cyclic group. We are taking group in the target group, and we have the attribute universe, the keyword universe, and we have assumed that each keyword is of binary type, and we have one hashing function we have used, which will take any binary string as input and will generate one element from ZP, which is a group of integers of prime order P, and that the length of the prime is determined by this security parameter. So basically here, the thing that we have to notice is, so for each attribute here in this, we have to assign a secret credential, some secret to all the nodes, and then later on we'll build this tree and reconstruct one from all these multiple secrets. So this is the thing that I want to show. So for each attribute, we selected one secret, and that will become the part of this master secret key. It's not available to everyone. But this is the master secret key, and rest of the things are the public parameters. Now here, this is one algorithm. Its detail I haven't mentioned here, but this algorithm will take this this set of secret values and the corresponding because is a bit tree algorithm. It will make the construct the corresponding to the policy. It will construct the access tree, and for that we have to reconstruct. In between, we have to add some dummy nodes because we want to make every internal node as a AND gate, and for that we have to add some dummy nodes. And for that, this assigned value algorithm will generate the secret for dummy nodes that we have to add in between. And finally, this is the thing that is of the key focus. It is the root secret. So from those multiple values, we constructed one value, and we'll be using that later. Uh, and that will actually help us in reducing the cost. So here, to generate the secret key, so it is now for all the attributes, we have just one root secret with us, and we use that to generate two components here, K1 and K2. And as you see here, that's that key number is always fixed, irrespective of the fact that we can have like any number of attributes in the access policy, but this number always stays fixed. It always stays. Okay, so this is how we have achieved the constant size secret key. The key is of size 2 only in here. And to encrypt the keyword, we have to use the attribute set. These are the attribute set or attributes possessed by the user. So these are taken into account. If we see here the ciphertext constant, here we have a component here, C3J, that varies proportionally to the number of attributes possessed by that. So the ciphertext size is not constant, but the secret size is constant. So we can later on try to uh, like figure out how we can make this constant as well. So that could be one improvement over this. Now for generating the trapdoor, this will take in I want to search a file that might contain this keyword, and you have to generate then the trapdoor for that keyword that will be later on used by the server to perform the search operation. Now, if we see here in uh, the trapdoor generation, so it also has four components. So it uses the secret key. So yeah, K1 and K2 as a component of the secret key. So they are in here. There's no other secret credential generate means this is the token generated by the valid or authentic user. This is how we ensure that we had to take in the secret components also, the secret key components. So here the size of the ciphertext is also fixed. It is variable of the number of attributes. And whenever that the search trapdoor or the token is given to the cloud server, then cloud server performs the search. But before that, it has to verify. In ciphertext, we have the policy, and here we have the attribute. It has to verify. Sorry, here we have the attribute, and here we have the policy. So this cloud server, like a double check, we are ensuring that the user can perform the search operation if and only if he or she is able to satisfy the policy. So what sure that if this just about that task, it will just return null, and it basically tells that that particular user is unauthorized to access it. So that's how that fine grainness is achieved. And later on, it performs several some certain computations. And if this condition holds, means if the trapdoor and the keyword for which the ciphertext is generated, if it matches, then only this condition will hold true. And when it holds true, so these are the pairing operations, bilinear pairing operations. So when this condition holds, so this means the keyword has matched, and the cloud server will return 1. Otherwise, if it has searched all the possible keywords and nowhere it is matched, then it will return 0, that no such file exists with the given keyword. So this is the basic idea, and these are the some of the results from that paper only, that we have able to make the key generation. Uh, the cost of the key generation is also the computation cost of generating the key is constant, means if you vary the number of attributes, it's not varying. And similarly, the computational cost for the trapdoor is also constant. And further, these are the some of the key highlights of this feature. It is the general access structure we have used. It's not like we have just and between in most in several attribute based encryption schemes sometimes, and based access policy is used, where we just have and between the attribute. But here we allow the general structure, means we can have anything between the attributes. It depends upon the threshold value. So it's the general structure that we have used. And here the size of the secret key is constant, and the size of the trapdoor is also constant. In all of the scheme, it is variable. It varies with respect to the number of attributes, but here it is constant. And this is the final calculations from that paper only. So storage cost of the secret key is just 2 group elements. So this is the size of the secret key. This is the size of the ciphertext. So it is variable. It depends upon the number of attributes. But here, if we see the size of the secret key and the trapdoor, it is constant. So in most of the scheme here, we do have the constant size trapdoor, but the secret key is variable. So we are able to achieve both the things. So that's how we can say the scheme is an efficient scheme. Now, we to reduce this inherent cost associated with attributes based searchable encryption schemes. So one approach is, we have just seen we have to make this cost and size independent of the number of attribute, and it has been the focus of many works since 2004. But there is another scheme. If we have some resource constrained devices, and for them we want to use the attribute based, means we want to use fine grainness also, and we want to ensure the privacy and everything. But we have a constraint that those devices are not very resource powerful. We have resource constrained devices, like in the if we talk about some healthcare network involving IoT devices, which take out uh, we have wearable devices which take in the our BP reading and all those things, and then we want to store our data to the cloud server, but we don't want to store that to the in the plain text form. We want to execute the scheme, but here we have a constraint that you cannot directly deploy these schemes into the resource constrained devices. So first thing, you if you want to do that, the first approach we have seen, okay, somehow you have to design your scheme in a way that it becomes invariable, means the size and the cost become invariable of the number of attributes. And the second thing what we can do is, we have means we don't want these resource constrained devices to execute these computationally intensive tasks by themselves, but we want to leverage certain technologies like the blockchain technology we have, which can improve both flexibility and which add lots of things to the scheme, means with its inherent properties we can achieve decentralization. It is like free from single point of failure. So we'll discuss all these things, means now we will be using blockchain technology to construct the attribute based searchable encryption scheme. So with the nodes in the blockchain network, we will be delegating some of the computationally intensive tasks to these nodes, and thereby we can achieve that a significant reduction in the cost. So that's our second agenda. And here, so these things we'll eventually discuss. These are the key features of our of this scheme. So here, whatever computationally intensive tasks like by linear pairing we are doing. So these are uh, take quite a lot of space and computational power. So these tasks we don't want the resource constrained device to perform by themselves, and we leverage the blockchain network for that. We want to delegate those tasks to these nodes on the network, to some of the nodes in the network, and it is free from the trusted authority, purely decentralized, because it is the key property of the blockchain technology. We don't have any central control. There is no single authority responsible for governing the system. The searchable encryption scheme developed using the blockchain technology inherits this fundamental property, and hence it results in a fully decentralized system. And it we have a reduction in these schemes are computationally efficient, and we have seen significant reduction in computational overhead, because the blockchain assisted searchable encryption scheme, the task specifically the task system initialization and the task of generating the search token, but not the complete search token. We only delegate some part of it, means from the blockchain we'll get only a partial search token, and thereby we can achieve reduction in computation also. And further, we can say it improves reliability, and since it is decentralized, so it is free from single point of failure. So these are the key features of our scheme. Now we are going to use blockchain, and specifically what blockchain, is it public, private, or something else? So we are going to answer that now. So first of all, what is a blockchain? As the name suggests, it is a chain of blocks, blockchain, chain of blocks. And how this chain is formed? This chain is formed and secured with the application of cryptography. So blockchain is basically a sequence of records, which is analogous to, so we have a sequence of records which is analogous to our traditional ledgers, but we have one additional property here that's called as immutability, and hence sometimes we call blockchain as immutable ledger also. Okay, now how they are secured basically. So whatever information we store here here in the block. So we compute a hash of that block and store that within the block. And how this block is linked to the next block. So every block contains the hash of the previous block. So if we make any change here in the data part or anywhere I disturb anything, so the hash of this block will be changed significantly. It's not like even a single bit is changed. So it will be uh, completely changed. The hash will be completely different. So if this hash is different, after manipulation, we did something here. So it will not match with the previous hash and the whole blockchain will become invalid and it will lead to an avalanche effect. That's how it is actually secured using the application of cryptography. Now, depending upon the requirement and application area, the responsibility of managing and updating this ledger, it can be given either to everyone in the blockchain network, like we usually have in the public blockchain platforms, like the Bitcoin network we have, or it could be given to one particular organization, like that is known as a private blockchain platform. The example of that could be that is Hyperledger. You might have heard that. And we could have a hybrid scenario where we have a selected set of users from different organizations with equal power. And we give that capability to only those set of users. And that is called as a consortium blockchain. And in our this particular scenario, in the cloud-based healthcare cyber physical system, we have designed one scheme. And in that scenario, the public blockchain platform does not seem quite suitable because it allows everyone to access everything on the system and the data involved may be sensitive in nature. So we don't want to risk that. I think the private blockchain platform that also does not fit in the considered scenario because it's too restrictive and there is still controlled by just one single authority who can manipulate the data for their own benefit. And therefore, the option that we have left with is the consortium blockchain, where different entities associated with the healthcare uh, makes basically a consortium and pre-decide the nodes from each means these are some pre-selected nodes that will participate later in the consensus means they will come to one agreement of deciding whether that block is valid or not. And by leveraging the benefits of consortium blockchain, we can impose control as well as we can enjoy the degree of freedom, the decided degree of freedom, we can say. And this is the basic architecture of the consortium blockchain in our scenario. So here we can have different institutions like the hospitals, we can have research institution, health ministry, insurance and pharmaceutical industries. And these organizations, they pre-select some set of nodes as a consensus node as per their governance policy. And these are designated nodes are the one that will participate in managing and updating that distributed ledger. And while other nodes, they can just contribute the data, but they cannot add the blocks to the blockchain. So only these nodes will be able to do that. And if the number of these consensus nodes, it will be more, then it will result into a more secure and fault tolerant schemes, because now more nodes have to be agreed to reach to the consensus. So that's basically some inherent thing that if we have more people, then we need uh, uh, means to come to a certain conclusion. So that would not be uh, that much easy. So it will make the scheme more robust. And here, there are the role of the blockchain is in 3 steps in the given scheme. So first of all, in the system setup phase, we are going to use the nodes of the blockchain. So these consensus nodes, we don't have any single trusted authority, centralized trusted third party. We don't have that. We have the consensus nodes. They will initialize the system, and now they will generate those global public parameters. And secondly, we have used this consortium blockchain for user registration and the generation of partial search tokens. Now here, any user can register themselves to the consortium blockchain, and they have to just send their public key corresponding to their unique ID, and it will be means that will be the task of assigning the secret credential will be done by those consensus node together, and will have in a secret key the multiple components given by each of the consensus node. So, and apart from that, it is also responsible for managing and generating the search tokens when the user want to retrieve some encrypted information from the cloud, so he or she can reach to the consortium blockchain to generate some means to basically we want to unburden the user from the great overhead of means we have to perform a lot of computation. So instead of doing that on their own, they can reach the blockchain to generate the partial search token corresponding to the attributes possessed by that user. And finally, it is we don't have to keep any master secret like we used to the trusted party used to hold earlier. So here we can just there is no single entity that manages the system. So this is another benefit we have. Now the general architecture, the system architecture. Now here, like I said earlier, also we used to have 4 entities. So here also we'll have 4 entities, but instead of the trusted authority, we have the consortium blockchain. Okay, so this is the consortium blockchain, and this entity will initialize the system, will generate the global parameter, it registers the user, uh, it registers every user corresponding to means to each user we have assigned here a unique global ID. It has a role in the construction part. So it registers the public key of every user, and when some user wants to perform search, then consortium blockchain will generate some will generate a partial search token for him. Later on, that will be used by that user, and it will add certain further some computation, perform certain computations to it, and then it will finally generate the complete search token. Now, this consortium blockchain, after that we have data owner. So data owner, as the name suggests, is the one who actually owns the data. So here in this scenario, we are considering the health data, and the data owner wants to share his or her health data to the to some third-party cloud server. But before outsourcing both the health data and uh, health data file and the associated keywords, we have to first encrypt them using now health data can be encrypted using any standard symmetric key encryption, but the for encrypting the keywords we have to use because we want to in the public key scenario we want sorry in the shared cloud storage environment we want to enable the search. So for that we are not going with the symmetric key, we have to use the, and further we want to do that in differential manner, so we are relying on the attribute based encryption for generating the index. So after encryption, everything is stored here at the cloud server, and the data user, yes, data user is the one who wants to access the data stored at the cloud server, and he or she will generate a search token for that, which is sent to the, so it is like earlier, we have to generate search token that is sent to the cloud server. And later on, this cloud server, which stores all the encrypted data. So the cloud server will perform the encrypted search on the behalf of data user and return the search result. So this is it. And if you look at the sequence, so we start with the system setup first. So the consortium blockchain initializes the system, generate the global parameter, and publish them. Then after that, every user, it could be data user or the means every cloud user, you can say data user or owner, they have to register onto the consortium blockchain by storing their public key, which is generated by them locally. And we have the data owner. So now in the third step, the data owner will generate the runs that gen index algorithm to generate ciphertext and keyword and upload everything here in the cloud server. And in the fourth step, if you see here, so to get the required data from the cloud server, the data user will send a search token request to the consortium blockchain. So it will not generate the search token by itself. So it will generate the request. Now it will send its credential, like it has some attributes associated with a particular user. So it will send those. So data user will send those attributes in that search token generation request, and using those, it will generate a partial search token, which will later then be sent to the data user. It will perform some additional things on it and generate the complete search token, which is given to the cloud server, and later on the search result based on that will be returned to the cloud user. And here we have just shown that each of the means the algorithm that is executed by each of the entity. So here at the blockchain part, we are executing two algorithms, the setup and partial token generation. So if we see here, it is taking the public key of the user. So each user has a unique global ID, and we have some global parameters, and it also takes some attribute set. That is it is the subset of the attribute universe, of course. So it will, using these, it will generate the partial search token, which will be then, this partial search token will be taken as input by the data user, and we have this complete token generation algorithm, and using the secret key of the user, which only that user will have, and now it will generate the search token for this keyword. So most of the computation task which involves all the attributes and doing lots of computation, that is done here by the blockchain, and only some simple calculations will be done by the data user. So this is one key advantage. And after that, whenever we have the complete search token, that is into the cloud user, and like I said, it will perform the search on the behalf. Now here, see, earlier we said that for generating the secret key, we use the access policy. Here, for generating the secret key, we use the, we see here, we have keygen algorithm. So this in the this setup algorithm, where it will means here we will associate the access policy with the ciphertext, and that's why this underlying logic that we are using is attribute based encryption for building the searchable encryption scheme. So here the policy is associated, this A is for the access policy, it is associated with the ciphertext. The ciphertext policy AI. Yeah. 11:55, 12:50, 40A, 45, 6. If I discuss the result here, we don't have a single authority here. We have multiple consensus nodes in this. We have ciphertext policy ABE, and the access policy that we have used is a monotone Boolean function. It is also a means tree type, a general structure we have here. It's not like we have just taken an AND operation between the attributes, and these are the security assumption. This is a decisional parallel binary entity element exponent assumption that we have used to construct the scheme. And these are the two related schemes, which are also means they also try to reduce the cost. So if we compare here, so among these schemes, the storage cost is we just have to store one element, and here is being for these two. So it is proportional to the number of attributes. The size, the number of attributes associated. So here, and similarly, the computational cost, we have to perform one exponent operation only. So this is also significantly reduced. And here, this is the partial token generation by the blockchain. So most of the task is done here, and we don't have to actually store this the complete token by the user. Every time we can reach here and generate the token, the search token for any keyword. And for the search also, we have constant number of pairing operations. So no, I'm sorry, that's not constant. That is a variable thing we have here. So the key task is that is performed by the blockchain is we have delegated some of the computationally intensive tasks to the blockchain so that the scheme can be easily implemented at the for the resource constrained devices. So we have seen so we haven't seen complete working because that will make the session quite lengthy. And the two schemes that we have discussed, they focused upon reducing the computational cost associated with the different algorithms, the computational as well as the storage cost. These are the two key things we are focused upon. And while constructing the schemes, as we have seen, security and efficiency. So we have a trade-off between the two. So if we want to make the scheme more secure, so that could be less efficient. So we have to decide our priorities and scheme accordingly. And so in the first scheme, we directly try to reduce the or make the storage and computational costing variable of the number of attributes. And in the second case, we didn't try to make it invariable, but instead what we have done is we have leveraged some other technology to perform the computationally intensive tasks. Yeah, reduce the cost.